It is challenging for global human motion recovery due to the complexity of human poses and dynamic interaction between humans and their environments. Unlike ground-based motions, such as running, climbing is an activity performed off-ground, where climbers use hands and feet to ascend holds or walls. As an important sport and recreation, the climbing race has become an efficient. Research on climbing motion capture is sparse, partly due to the limited availability of climbing datasets. As a result, the research community lacks an in-depth understanding of challenging climbing motions. To address the data insufficiency, we collect Ascend Motion, a large-scale and challenging climbing motion multimodal dataset. Ascend Motion includes the motions of 22 skilled climbers climbing 12 different rock walls. It includes rich modalities from hardware time-synchronized devices. Moreover, it consists of the global trajectories of climbers, which are important for understanding human motions in world coordinates. We also combine automatic annotation with manual refinement to ensure the accuracy of the Ascend Motion hardware acquisition system integrates multiple sensors and can be used for acquisition in real rock climb. The LiDAR captures a 3D dynamic point cloud at 20 frames per second, while the RGB camera is down-sampled to the same frame rate. The devices are synchronized via the Precision Time Protocol. We use a CallShark Auto 66 unit as a master clock and send PTP slave clocks to the RGB camera and LiDAR. The actions collected in Ascend Motion are from skilled climbers. They can scale rock faster for longer periods of time and grab more holds than amateurs. The annotation pipeline is important for high-quality datasets. In multimodal data pre-processing stage, we register the LiDAR point cloud with a high-precision scan scene. Then we transform each modality data into world coordinates and perform frame-level calibration between RGB, LiDAR, and IMU. In global optimization stage, we apply two main laws to achieve accurate and natural human motion data consistent with the scene. The global refit loss promotes precise global alignment between the SMPL model and the point clouds. And scene touch loss prevents unrealistic intersections between the SMPL model and the scene mesh by measuring the penetration depth between the vertices. To further improve the dataset quality, we use the SMPL annotation tool for enhanced labeling of sequences. We engage for observers to review the automatically annotated results. For any ambiguous limb movements observed in RGB views, we perform additional manual adjustments and mark these frames as keyframes. Finally, we propagate poses from multiple keyframes within each sequence to ensure global consistency in both smoothness and accuracy of the poses. The ClimbingCap pipeline consists of 3 parts. The first stage extracts features from the RGB sequence and the LiDAR point clouds, predicts the poses in camera coordinates and the positions in global coordinates by camera coordinate decoder and global The post-processing stage consists of 3 optimization-based losses. These losses optimize global human motion via limb weights, spatial positions, and spatial velocities. Ascend Motion also contains some unlabeled data. In order to make reasonable use of this data, we designed a semi-supervised network to process this type of data. The student model clones the parameters of the teacher model. During semi-supervised training, the teacher model estimates the pose labels from the unlabeled motion data and uses the pose labels as pseudo-labels to further train. In the first part of the experiment, in order to quantitatively evaluate the annotation quality of Ascend Motion, we performed an ablation study on the different losses mentioned in the annotation process. The error metrics are small, which proves the effectiveness of the global optimization process and the high quality. In the second part of the experiments, to evaluate the performance of various state-of-the-art HMR methods on the Ascend Motion dataset, we divide the scenes into horizontal and vertical according to the main directions of human motion. Compared with horizontal scenes, vertical scenes pose greater challenges to both climbers and HMR methods. In vertical scenes, ClimbingCap significantly outperforms all other methods, including the second-ranked method GVA. To test the generalization ability of all the HMR methods, we evaluate their performance in the CME4D climbing dataset without retraining or fine-tuning. The CME4D dataset consists mostly horizontal scenes, and the motions are less challenging than Ascend Motion. ClimbingCap performs the best in the CME4D dataset for most of the metrics, except in the qualitative experiments section, we visualize the results of various methods in 2 coordinate systems. WAM and GVHMR perform well in terms of camera coordinate metrics, but perform poorly in terms of world coordinate metrics. 4 vertical scenes, ClimbingCap performs the best, significantly outperforming the second best method. LiDAR-based and other LiDAR plus RGB-based methods perform worse than ClimbingCap. These methods do not fully consider the global trajectory. The results show the importance of considering the relationship between camera coordinates and global coordinates. We also conduct additional trajectory qualitative experiments for the results of global trajectory estimation. ClimbingCap is closest to the trajectory of ground. Finally, we show in the wild data results on non-marker scene. Thanks for watching.